Hello everyone, I'm Yuxuan Yang from Örebro University, Sweden. I'm going to present my workshop paper, Learn to Predict Posterior Probability in Particle Field Theory for Tracking Deformable Linear Objects. We proposed a deformable linear objects tracking framework using particle filtering with a posterior probability predictor. So we do not rely on color-based segmentation, which is required for many related work. With the posterior probability predictor, which is a neural network, it is easy to do parallelization, and then it's more efficient. We can have more particles in the particle filtering, which lead to better tracking results. Predictor is a neural network which is differentiable. It's easy to get gradients information, and we can use this information to improve the motion model, which is a very important part in the particle filtering. For some of you might have no idea what deformable linear objects are. They are objects like ropes, cables, hoses, wires, which are common in our daily life. They are also very common in many robot manipulation tasks, like rope knotting, insertion, or even perform actuators in soft robots or continuum robots. Therefore, we need to control DLOs to complete these tasks, and we need perception. We need to track DLOs for achieving feedback control. However, as you can see in the images, local distinctive features or appearance on the DLO and the object's high-dimensional state space make tracking challenging and still an open question in robotics. Particle filtering is a common solution for rigid object tracking, where it cannot be directly applied to DLO state tracking because of the large number of particles it needs for sampling in the high-dimensional state space. Our previous work uses a particle filter to track a DLO by sampling in a learned low-dimensional latent state space, where the latent state space is acquired by training an autoencoder. The tracking starts with some particles. Here, each particle is a proposed latent state of DLO. We update the latent state by a motion model, which predicts how latent state will change at one time step. With the new latent state, we reconstruct DLOs using trained decoder. And together with the observation, we calculate observation likelihood or posterior probability of each particle. Then we sample particles. Basically, with larger probability, the particles are more likely to survive to the next iteration. In this paper, instead of handcraft way to calculate the posterior probability, we try to directly predict it through learning. We use some pre-trained image decoder to extract the image features of the DLOs. Then we concatenate DLO latent state with image features respectively and predict how likely the proposed latent state is given the observed image. By doing this, we do not need pre-processed or masking DLOs. The pre-trained image encoder takes care of this in some way. We can do parallelization easily thanks to the neural network, and we can use the GPU to accelerate the process. And also, the neural network is differentiable. We could use the gradient information to improve the motion model. We need the motion model to update the particles at each time step. We use a multivariate normal distribution to describe the motion model to approximate the probability distribution propagation of the latent state. For the constant velocity model we used in our previous work, we assume the latent state changes smoothly. Now, since you have the gradient information, the gradient of the posterior probability with respect to the latent state, we can leverage this information to improve the motion model. Here we are showing one qualitative result. It is only a preliminary result. It is not perfect. This is a proof of concept showing our proposed tracking method works in a simplified scenario. Here we are simply showing when the initial state is unknown, the tracking can reach faster using motion model with gradients information than just using constant velocity motion model. This brings us to the end of my presentation. Thanks for your attention.